Yeah, good afternoon, guys. Yeah, so we'll continue from last class. Okay, so in the materials joining laboratory. Quick summary about last class what we are seeing. So we are looking at friction stir welding, right? So friction stir welding was demonstrated in last class. So you must have already submitted the report. So those who are not submitted, make sure that you submit anyway. If you submit late, so you may lose some marks for the evaluation. Okay, in the last week demonstration, you were looking at the effect of process parameters on the bead geometry, right? So you were looking at the effect of welding speed, okay, and the effect of pin geometry by changing from one pin shoulder and the pin combination to other combination, how the weld bead geometry evolves, okay. And we were also looking at some of the other variants, like how friction stir process welding also can be used for simple processing, doing a bead on plate. So that bead on plate deposition what we carried out can also be made into an additive manufacturing process. Okay, so we can also make the tool as a consumable. Tool can be made to stick to the plate. So when we actually stir the tool intensely gets worn out and deposited onto the substrate. So we can also make it layer by layer. Okay, so one company came up with additive manufacturing using friction stir welding based. It's called MELD, M-E-L-D. Okay, so they do make use of friction stir processing as a way of creating objects, layer by layer. And this technique, like depositing the tool, okay, on top of an object, is also used for repair. Okay, so the worn out parts can be repaired after service exposure. Okay, so you must be now aware of the process. If you have any questions in last class, so you can ask now. Yeah, otherwise we'll move on to today's demonstration. Okay, anyway, so we'll continue. So today we are going to look at resistance spot welding. So in resistance spot welding, so what we are going to do is, again, we first look at the equipment, what we have. So we have two types of equipment. So one is the conventional resistance spot welding, and other one is some advanced variant of resistance spot welding. It's called delta spot. In this class, demonstration class, we are going to do a lot of welds, okay, because resistance spot welding is one of the shortest welding process in terms of time. So it doesn't matter, this recording anyway I'm not going to use. I'll use the GoPro, okay, not a problem. So the resistance spot welding, we are going to carry out, okay, welding to demonstrate three important process parameters. How these parameters are going to influence the welding process. Before going into the detail about the welding process parameters, okay, so almost all of you must be familiar with spot welding, isn't it? So if you are not really familiar, I'll just quickly share, because this is one of the unique processes. You may have to recall quickly. Let me share this slide. Okay, so for the sake of doing it, I'll just explain. So where we weld thin sheets in this process, okay, so typically in the ranging from about 500 micron, 0.5 mm to 3 to 4 mm maximum, by using, okay, two electrodes and passing electric current through these electrodes, which are actually, okay, used as a medium to conduct, okay, electricity towards the faying interfaces. Say for example here, the schematic I show. So we have one top electrode and bottom electrode. Okay, so both the electrodes are typically made of copper to ensure that proper electrical conductivity is made. And these two electrodes are all water cooled. Okay, so therefore the electrodes don't heat up when we actually pass the current. So we keep the plates to be welded or sheets to be welded, okay, in overlap configuration. So what is overlap configuration? So top of each other in a lap, for instance. So something like this. And the electrodes are used to keep these sheets in position, and we pass the current. So when we pass the current, what happens? Okay, due to the various resistance that are present in the circuit. Okay, so we generate heat by Joule heating. So if you look at the conventional, circuit, what I show here in the slide, okay, and you may also see that there are a number of resistance present, okay, in the circuit. There, okay, the resistance between the two interfaces to be joined, like this is sheet on top and sheet on the bottom, at the interface between these two sheets. Okay, so you see here, and that's where the maximum heat is generated because of the contact resistance between the interfaces. Okay, and you may also see that bulk resistance like R1 of the electrode is negligible because we use copper. The bulk resistance of the sheet R3, okay, what is denoted here, it's also negligible compared to the contact resistance, okay, at the interface. And there are also two more resistance, the contact resistance between the top sheet, okay, and the electrode. Similarly, the contact resistance between the bottom sheet and the electrode, okay. They don't really contribute to the heat generation welding. Why? Because so we cool the electrode effectively by water, so we extract the heat that are generated at the top and bottom sheet. So if you look at all the resistance, you may always see that the contact resistance between the sheet to be welded would determine the heat generation. So you may also see that, okay, the moment we pass the current due to the contact resistance in this process, the interface would start melting, and then we create a liquid pool, what we know as nugget in this process. So well nugget would form due to the heating at the interface, and then once nugget solidifies, so we create a button, okay, which is what we know as well nugget. Okay. So if you look at this process, the basic principle in heat generation is due to the Joule heating, I square R, and R is predominantly resistance determined by this contact resistance. So what are the important process parameters then? So then the current, okay, and then time at which we pass the current, okay, welding time, and the pressure we apply through the electrode, the load we apply. Why? Because the load would indirectly change the contact resistance. More the load, okay, less will be the contact resistance. Okay, so therefore the load would indirectly affect the well nugget diameter, right? So if you increase the load, resistance decreases, okay, so therefore nugget will decrease for a given welding current and time. Okay, so in this class what we are going to do is, so we are going to show you how these three fundamental process parameters, the welding current, welding time, and the load we apply through electrodes would influence the weld nugget diameter, the weld size, okay, and we also demonstrate some basics process development procedure, what is known as weld growth curve. Okay, so what are the weld growth curves? So weld growth curves are the process maps we use to identify what would be the optimal welding current, welding time, and welding load to achieve a defined weld nugget diameter. So for example, here we have plotted weld nugget diameter as a function of, okay, the tensile shear force. Okay, so we also carry out after welding tensile testing. Okay, so in two ways, in a lap shear mode and cross tension mode. Okay, so what is a lap shear test? Okay, so we weld. Okay, so sorry, in two overlapping configuration. Okay, so one we see here. So in this configuration, and we apply a tensile stress, tensile load, and we identify what will be the strength, what will load is required to break this joint. Okay, so then from that we can identify what would be the tensile strength, and we can also create cross tension samples. Okay, so like cruciform shape, and we pull it in a tensile test, and then we identify again strength. So in these two configurations, we can also weld and identify, okay, so these parameters, and we also show a demonstration about how we can do the samples preparation by lap shear and the cross tension test, and as a function of three parameters: welding current, okay, welding time, and weld load, how these graphs evolve. Okay, the evolution of weld nugget diameter as a function of three parameters, these three fundamental parameters. So we have, as I said, two processes. Okay, so one is the conventional resistance spot welding, and other one is a delta spot. Okay, so in delta spot we don't use solid copper electrodes, whereas we use some strip electrodes. And that process, when you use a strip electrode instead of solid electrode, okay, so we have copper strips which are consumable, so which can be changed for each weld. And by doing so, we can also use the R2 resistance between the thin foil electrode and the top surface, also for generating heat. So we can enhance, okay, the welding, or you can increase the weld nugget diameter for given current. Another way, okay, in delta spot resistance spot welding process, so we can create, okay, an equal weld nugget diameter for much less current and lower welding time than the conventional spot weld. Okay, we will also show that, okay, as a demonstration how that equipment looks like. Okay, and in both the process, okay, we will show you some of the weld growth curves. So what are the weld growth curves? Is nothing but, so we plot weld nugget diameter or weld size as a function of current, welding time, okay, and the load. So as a function of current and welding time, weld nugget diameter should increase, isn't it? As a function of load, okay, so when you increase the load, okay, so weld nugget diameter would decrease. So other way around. Okay, so this is for time and current, and this is for load. Okay, so these curves are known as weld nugget, weld growth curves. Okay, so our technicians and the TAs would show you, okay, how the weld process develops, weld nugget diameter evolves by changing welding current and welding time. Okay, so this is what we are going to look at in this class. If you have any questions, we can ask. Otherwise, you may also ask when the class is actually taking place. Okay, is that clear? Okay, what we are going to look at today? Okay, to summarize, we are going to look at resistance spot welding. So we will do the demonstration in a conventional resistance spot weld to show the effect of three important process parameters: welding current, welding time, and the load we apply through electrodes. And we will also show the weld growth curves, okay, how we develop. And after looking at all these demonstrations, we will move on to the delta spot, where we use consumable strip electrodes, okay, instead of solid copper electrodes. Okay, good. So we'll move on. So I'll hand over to our TAs and technicians, and then I'll be around for some time. So I've got a meeting at 3. Okay, so maybe I'll come back when during summary. Yeah. Yeah, Prakash.
Thank you.
Yeah. So this video will be there. Jack Wilson. Yeah. So you can look at the Jack survey screen.
Shall I go?
Yeah.
Good afternoon, students. I'm audible? Hello? Right. So my voice is okay? Because I have the Wi-Fi net is not good. So my voice is clear? Hello?
Yes.
Right. Okay. So welcome to our material joining lab class. For today's lab class, we are going to see one of the very good welding processes. It's called an resistance spot welding process. We have two equipments. One is the resistance spot welding conventional. Another one is the modified version of conventional resistance spot welding. It's called an delta spot. So let's go into our today's lab class. Hope our Professor Murugan had explained you in detail about the working principle of our resistance spot welding. So even then also we will let us know in detail. So first let's see the conventional resistance spot welding. So we have a resistance spot welding which is indigenously manufactured from India. It's a company called Nash Robotics, and the capacity of this machine is it will go to maximum 100 kVA capacity, and maximum of 5 mm thick plates you can join. So both the plates joined together, it can be 2.5 mm plus 2.5 mm, maximum to 5 mm plate you can join with this machine. So if you are closely look into the machine, how it has got constructed, we have two copper electrodes in which I'll keep the two materials in between, and I'll apply a pressure from top. The pressure is applied by means of pneumatic cylinder. Here we have. So we have which is connected to our air compressor unit. So with that we are applying a pressure. So you can control the air pressure, how much pressure for your weld joint is required. You can vary that. With that pressure is this the top electrode will come down and it will be applied. Pressure is applied, and then after the current is passing through the plate. So with that, with the weld time we give, so the resistance spot is getting joined.
So water cooling it in.
Yeah. So here to cool the copper electrodes and the other electronic components, we have a cooling water supply which is going into the copper electrode and coming out. Same time it is going to the other switch. Okay, right. So let's go into the welding resistance spot welding process parameter. As our professor said that the resistant spot welding itself name, it says that works in the principle of Joule's heating. So when I talk about the Joule's heating, the resistance also will come into picture. So when I talk about the resistance, the current plays the major role. So in the sense, the resistance spot welding is typically used for joining of two metallic materials. Audible?
This V is not.
Okay, so it is made of.
The voice is breaking.
Okay.
connect to global network.
Now I am audible?
Yeah.
It's okay? Right. So right. So let's see. So it's okay? Okay, so let's see how this machine is constructed. The machine is connected to a three-phase power supply. Inside you have a transformer, and then we have a microcontroller which is plays an electronic parts, and for measuring the current we have a current sensor here which is connected, current sensor. Okay, and to set the parameters like the current and the weld time, so we normally say weld time in terms of cycles. So to set that parameters we have an electronically control, and to check whether I have applied my load, it is in pressure, it is, we have a pressure sensor also which gives the displays of my sensors. Right. So this side, just come here, sir. Okay. So before joining our plates, how to choose the parameters? So here you can see the sticker on our machine which will guide you. So depends on your thickness of your plates. This is from an American Welding Society or from IIW, Indian Institute of Welding, which gives you a guidelines what current, what pressure, and what is the weld time you have to choose. This will give you. So right now I am going to use a 1 mm thick plate. So I am going to use a my electrode diameter is about 16 millimeter outer diameter, and minimum is the 6.3. So I am going to use 6 millimeter diameter electrode tip, and cycles about 20 to 15 to 20 cycles I am going to use weld time, and current I am going to use is about 6000 to 8000 amps I am going to use. So I am going to vary the current, and the pressure I am going to use is 3.5 kilonewton. So I will vary the pressure from 2.5 kilonewton to 3.5 kilonewton. Okay, so this table gives you a guidelines for how to set the parameters. These parameters are set for our mild steel plate. So for our lab class I am going to use a it is a DP 980 steel sheets. So I have it is our one of our research scholar is used for her research purpose. Let's see how it can be done. As our Professor Murugan said that, you can show it here, sir. We can join in two types. One is the lap shear, and one cross tension also. We have made a zig for that. So this one, what we use the zig for our lap shear. So I'll keep one plate and another plate over that, and here we made another zig for our cross tension plate. So at the end, whenever we want to evaluate at the end for the mechanical properties or whatever it is, so we can do in these two fashion. And of course one more is the what is that, sir? One more bed.
The L.
L. So L normally we don't do it. So this is the two things we normally follow in our experimental purpose. Let's see how we can join these two plates.
Yeah, so just before that, the welding cycle Ms. Rangan was telling about, right? So the time we declare, we define in terms of cycles. You know what is that? How do you define that as cycle? So suppose if you use the resistance spot welding, almost all the cases we use alternating current. Okay, there is a problem in using direct current. So when you use alternating current, we will have to define the frequency. Suppose if you use 50 hertz, so then there will be 50 cycles, okay, per second. So Mr. Sankan was talking about 20 cycles. Okay, so if you use 20 cycles, so what happens? So that you can define them the time required, for welding. The welding duration, if you define in cycle, you also know indirectly what will be the frequency of the process, the current we are using. Okay, so suppose if you are using a 50 hertz alternating current and you weld it for 50 cycles, so the welding time will be 1 second. Okay, so it's extremely rapid process. You don't need to do the current of 7,000 amperes, okay, 7 kiloampere, so over 1 second, then it will be expelled. Expulsion may take place. The weld magnet will not be intact. Okay, so we can identify from the weld growth curve what is the maximum current, okay, above which this expulsion takes place. Okay, that is what we call Imax. So we do it until Imax, okay, and then come down and identify, okay, predefined weld nugget size. In automotive standards, the required weld nugget what you want to create, the size is 4 to 5 times of square root of combined thickness. Okay, so imagine if you are welding of 1 mm sheet, 2 of them, okay, so square root of 2 into 1.14, okay, times 4. So roughly we may have about 4.5 to 5 mm weld nugget to meet the service load. Almost the main application for resistance spot welding is automotive industry. Okay, where the thin sheets are welded. If you look at your car, you open the door, you look at the door frame. A lot of small dots in making. Those are resistance spot welds. Okay, so therefore the standard what we say, the 4 to 5 times square root of combined thickness of the sheet is all coming from automotive industry. Okay? And the other thing you need to make sure that these sheets, steel sheets what we weld, they are all galvanized. Okay, so galvanized means they must have a zinc coating somehow. Okay, so when we do resistance spot welding of zinc coated sheets, we use copper electrodes, isn't it? So the copper and zinc may interact metallurgically. So zinc may mix to copper, and we may form a brass layer on the electrode surface. So if you do continuously welding, we may also change the electrical contact resistance and the resistance, the bulk resistance of the electrode. So that would influence the welding process because you change the resistance in the circuit, isn't it? So over the time, after say 10 welds if you do.
Okay. So
Quickly we were discussing about the electrode erosion. So because of the fact that the zinc from the galvanized layer can react with the copper and then form brass. Okay, so to avoid that, we cannot, difficult to avoid, right? So to avoid that, we developed this delta spot, where we use strip electrodes, and then we can use every time a fresh spot of the electrode surface. Okay, and other than that, it also gives additional contact resistance between the strip and the top and bottom surface of the plate. Unlike here, where the contact resistance between the electrode surface and the top and bottom sheet is not really used to do the work welding because it's water cooled. So the heat generated the contact resistance between the electrode surface and the sheet is taken out. Okay, effectively. Only the contact resistance between the sheets are used to do the welding. Okay. Go ahead, sir.
Okay. So now let us go into our resistance spot welding. So I have taken 2 sheets. So I am not going to do a lap joint like lap shear test or the cross tension test. I am not going to do that. So for that initially I have to optimize the parameter. So I have to optimize the parameter. I am going to use a 2 parallel sheet so that I can use different parameters and I can use it at one sheet. I'm going to join 3 spots. I'm going to make it. Let's see how it goes. Right now I have set my So 8 kilo amps, and my weld cycle is 20 cycles. So this is what I am going to do that. So my current is 8 kilo amps, and my weld cycle is going to be 20 cycles, and my pressure is almost 3.9 kilonewton. Okay, see how it is done. Sorry,
Go ahead.
yeah, please.
You can summarize it.
So you can join 2 joint பண்ணுங்க. Okay.
lap shape
Lap here. Last. Okay. GoPro ready னாக்கா சொல்லுங்கண்ணா. வாங்க சார்.
கொஞ்சம் தூரம் வந்துருக்கா
ஓகே.
ஓகே கொஞ்சம் கேமரா கவராக கொஞ்சம்
ஒரு நிமிஷம் சூர்யாண்ணா. ரெடின்னா சொல்லுங்க.
ஓகே ஓகே
Okay, ready? So, right. So the parameter what we have chosen is 8 kilo amps and 3.9 kilonewton our pressure force, and weld cycle is 20 cycles. So 20 cycles means almost 400 milliseconds we have given for our welding time we have given. So for this plate it is a optimal parameter, I can say that. So I am going to change the parameter to 1 after 1. So I am going to decrease the weld current to 6 kilo amps. So 6 kilo amps per kiloma. Okay, so I am changing only the 6 kilo amps. Let's see how the weld joint is going to be. Right, you can see that there is not much effect, but I have got 6 kilo amps applied onto that. Okay, so let's go to higher one. Eight the last time. Kept
9 10
9. I think it is very high. Polama?
போகலாம் சார் 9 தான் லாஸ்ட்டு போகலாம் போதா
Okay, let's see. So you can see the you can see the flash. Okay, so you can okay, so this is how the parameters are optimized with different parameters. One is the very less current. We have used 6 kilo amps, and the 8 kilo amps we have done, and another one is the 10 kilo amps we have done. So when I go for an higher current, there is going to be a flashes, and you can see a more depth. So the pressure is also applied more pressure. The plate thickness is also reduced. So these are the three parameters I used. So let's see what kind of effect will be there for changing the weld time. So I will reduce the So I have made to 15 cycles and 8 kilo amps. The pressure I am going to wear a plate.
No, again it is in 10 kilo amps.
Sir?
Yeah, you can use 10.
No. It is the previous value. It shows previous value. But right now
What is this, sir?
I have 8 and 15. 15 cycles. Right now I am giving 15 cycles and 8 kilo amps. But the pressure is going to be same, 3.9 kilometer. Let's see. Please, sir. Start. Okay. So almost right. So we just show. This is 20 cycles and this one is 15 cycles. Almost I have a same. Okay, so you cannot take out. Okay, so let's try with different parameters. So I am going to decrease the pressure also. Pressure with the same current. Let's try with the different pressure.
வீட்டில் போட்டோமா
எவ்வளோ இருக்கு?
380
இப்போ
250 40 30 20
ரிலீஸ் பண்ணுங்க.
220 220
300 kilonewton இருக்கா?
Okay. Increasing, okay, actually it's not showing the exact value.
Right. So let's try with the different cycles. I have an 8 kilo amps and 15 cycles, and pressure is reduced to 3 kilonewton. Let's see how this goes. Okay, so there is a little difference. It's not much. The thickness of material is little higher comparing to the previous one. You can see the depth of the spot is more here, whereas the recent one is not much depth. You can see. Okay, right?
How much force you are using?
So let's have a poor joint.
Same thickness sheet, sir.
Okay.
Your thickness is higher.
Right. இதே எடுத்துக்கோங்கப்பா, அது போடாது, அப்புறம் அதை வச்சு போட்டுக்கலாம். இதுதானே?
அதுதான்
இது போட்டு இது போடாத, இதையே போடு.
சரி சார் அதுவேவா
ஆமாம், அப்படியே போடு.
நான் அதிலே அடிச்சுக்கலாமே
அடி, அப்புறம் போட்டுக்கோ. கடைசியில் ஒரு பேராமீட்டர் போட்டு அடிக்கிறதுக்கு தான் அது வச்சுருக்காங்க. Okay, so now I have reduced to 6 kiloamps. Okay, so you can see, and it's not joined properly, so there is no current is not sufficient for to join these plates. So I cannot go beyond 8 kiloamps because I am going to get the flashes out. So that once the flashes comes out means that indicates that it is a high current. High current. So we should not. That indicates we should not go beyond the limit. So the optimum current I can say right now for this plate is 8 kiloamps. 8 kiloamps. And as our Professor Murugan said, to get the weld nugget diameter, we have to do a different parameter. We have to optimization, and then we have to how to check whether our nugget diameter is good or bad. So, for example, I have a thickness of 1 mm plate material. So 1 plus 1 2 mm. So when I say that my weld nugget diameter is supposed to be 4 into root 2. So if if almost it comes to 1.414,
Yes, sir. 1.414 into
414 into 4. So if you done it comes to around 5 point something the millimeter diameter will come. So if I measure that, if it is going to be almost 6 mm we have to get. So for 10 mm, where is that 10 mm? So 10 mm, 10 kiloamps for that we have got a more than 6 millimeter nugget diameter. It is not good for our welding processes. So it should be 4 into root T. So the T is the nothing but your plate thickness. So total plate thickness. So total plate thickness is 1 plus 1 2 mm. So this is what we have to optimize for 4 into root T. And the diameter of our the electrode how to choose is 5 into root T. So that's what we have to, our Professor Murugan was saying. The diameter is almost 6.2 or 6.3 millimeter diameter we got the electrode. Okay? Right? Shall we go into our next thing? Okay, so far the resistance spot weld joint we had seen that to optimize the resistance spot welding parameters. But once we have optimized the parameter, we have to go for either a characterization work. For that either we go for a lap shear joint or a cross tension joint. So we have made a zig for lap shear joint. So need not to actually in real these two have to join like this. So we have to join the lap joint like this. We have to join and we have to do that. Okay. So when we are doing that, there is a possibility of mismatch. There is a possibility of mismatch. So to avoid that mismatch, so we are using a zig. So we have made in a wooden structure. So and we have exactly we place onto that above one over other, and we fix onto the machine. It should go here. Huh? ये बड़ा होगा शायद पर okay, right? So this exactly fits, and I will use the optimum parameter. Time increase
8 kiloamps, sir.
I will reach to 24 cycles. Okay, sides. So let's see, we are going to join a lap shear joint. Okay. Right. You can see how nicely we have joined the lap shear. This we can put it in our UTM machine, and we can check for our tension test whether we will have where the crack or where the fracture initiates. It will give you a idea for the characterization work. So let's see into the another joint, cross tension. We have to do the cross tension, the zig we have. So cross tension will be like this. So either it will be pulled in this direction and this will be pulled in this direction. So you can use the cross tension, but this is for delta spot. This is for delta spot. Okay. Somehow you can use it. Okay. The same parameter you can transfer from you ready? Okay. Port parallel. வந்தாலும் பரவாயில்ல. Okay, so this is the cross tension as well as our lap shear joint. So with same parameters you can use this for cross tension and this is for lap shear joint. Okay, right. So I was talking about we are joining the two plates of dual phase steel. So now I am going to talk about the real metallurgically application. So we all know that dual phase steel will have a composition of ferrite and martensite. When I doing a resistance spot welding, so what happens during finding these two copper electrodes are cooled by our water cooling chiller unit. So while welding, the current is passing through that, and then after the weld is over, that will be cooled very fast. So whatever the microstructure is there in base material like the ferrite and martensite, due to high cooling rate, that weld region, the weld nugget will become a full martensite because of high cooling rate. So to overcome that martensite, that means I want to bring the ferrite phase also into the weld region, that is in weld nugget, weld region. So in general, normally what we do, we reheat that phase actually. We reheat that portion so that a little bit of ferrite will come into picture. So now what I am going to do is I am going to apply a secondary heating cycle, so that first cycle I will have a weld thermal cycle, second one will have a thermal cycle, which is a tempering effect will be there. So not to the weld thermal cycle, but it will be less than your weld thermal cycle. Let's see how it will be done. That means I am going to give two thermal cycles. Let's see how it is done with this experiment. So I have first thermal cycle I have used 8 kiloamps, and in second thermal cycle I will give little I'll give 12 cycle, and amps I will give about Oh my God. So I give 4 kiloamps secondary cycle. So I don't want to go to a thermal welded thermal cycle. So I have given 8 kiloamps and 4 kiloamps as thermal cycle, secondary thermal cycle. Let's see how this is done. So for this I have given 12 cycles and 24 cycles, so that it will give me okay. So once it is done, then after we can show. Ready? Right. You can see here, first cycle I have given 8 kiloamps and second cycle I have given 4 kiloamps. So I have given 2 thermal cycles. So in this 2 thermal cycles I have given. So the secondary thermal cycle, which is nothing but your tempering effect, will be there. So that we can bring our ferrite phase also into a welded result. So this is one of our very good example for our metallurgically I can say that. Okay, right? Okay, so let's any questions so far? Hello students, any questions? I'm audible.
They are sleeping.
Okay. Okay, whatever it is, let's go into our next thing. Right. So whenever I do a resistance spot welding for about few joints, finally my electrodes will end up into this kind of position. Okay, that is going to be a wear and tear of my electrode. You can see here we have it was stick to the plate itself, and you can see here almost it was joined, and sometimes it was plunged into our plate itself. Okay, so for certain joining of our resistance spot welding, you have to dress the electrode. So that means you have to machine it. So every time you have to do that. So to avoid this kind of problems, we are going for a delta spot welding. So let's go into our delta spot welding. Let's see the design of our electrode, how we have done. We have same copper electrodes, both the top and bottom. On top of the electrode we have a strip. This is a strip. So we have a strip on upper and bottom. So the strips are made of mild steel, copper coated. Copper will give you a good electrical conductivity, and every spot the strip will be moved forward, so that whenever you do a new welding, resistance spot welding, the new face of your copper strip will come into picture, so that the weld of our the electrode, the wear of electrode will be reduced in this. So number one advantage. And number two advantage of having a delta spot is, for applying a pressure, for applying a force, we are using a pneumatic for our conventional resistance spot welding, whereas here we are using a DC servo motor. It is a motorized control. It is a motorized control, and you will have a very precision control. Precision control. So that is the one greatest advantage we have with this machine. And also the delta spot welding is mainly used for welding of aluminum alloy. So welding of aluminum alloy with the resistance spot welding will take very high current, whereas in our delta spot welding it will be give you a good joint also. And also in our normal conventional resistance spot welding, we are normally joining two plates, but here you can join three plates. Three plates you can join. Sir, on the plate, pass it, sir. Move on. So you can see the typical joining of three plates. So 1 and 2, and center you have this. So these two, so 3 joints have done. That is the advantage of this delta spot. So 3 joints we have here. So 3 plates have joined with our delta spot. So this is the aluminum plate we have. And while comparing to resistance spot welding, conventional and delta spot, this consumes less current also. Less current. And in fact, we have a computer control which you can give you a graphical user interface. Graphical user interface where you can set your current, the pressure and the weld time will give you in a form of waveforms you can give. So that is the advantage we have. So right now we could not switch on our delta spot welding equipment. So in fact we need a little bit of software upgradation in this equipment. So sorry, we could not able to switch on this machine. So these are all the advantages we have with our delta spot resistance spot welding equipment. Okay. Anyhow, we have Murugan sir has got a nice research scholar, Vidhu Paul. Okay. So she is the one who doing and continuing her research with our delta spot welding equipment, resistance spot welding. I would like to say special thanks to Vidhu Paul madam, and of course she is doing a great job with our conventional resistance spot welding also. So any questions you are free to ask. So hopefully our professor will come back.
No, sir. He asked you to wind up the class.
Okay. Yes, sir. No, actually the tooling and all we don't want. Actually in a real case, for our own convenience, we can have our own tool diameter, whatever we want. Right now what we have is one conventional tool we have. You can have a different tool also. You have to take out, you have to okay.